Right now, floating invisibly around you, there is water. Not a metaphor, not a figure of speech. The atmosphere contains 12,900 cubic kilometers of fresh water, a volume comparable to all the renewable liquid fresh water on every inhabited continent combined. It is literally in the air you are breathing, and for centuries, engineers, ancient civilizations, and even desert insects have been pulling it out of thin air. No pump, no well, no plumbing. The commercial versions of this technology sell for $2,000 to $30,000, but the physics is the same whether you spend $30,000 or $12,000. This is the story of atmospheric water harvesting, the simplest technology you have never been taught, and why the cheapest version of it has been quietly ignored. Let us start with the science, because once you understand it, everything else becomes obvious. All air contains water vapor. Even desert air sitting at 30% humidity holds harvestable moisture. The key concept is the dew point, the temperature at which air becomes fully saturated and water condenses out onto any available surface. At 20 degrees Celsius and 80% relative humidity, you only need to cool a surface down to about 16 degrees to start collecting water. For every single degree Celsius of difference between the dew point and the air temperature, relative humidity shifts by roughly 5%. Reverse that principle. Cool a surface just a few degrees below the dew point, and water literally appears out of nowhere. This is exactly what happens when dew forms on your car windshield overnight. That is not magic. It is thermodynamics you can exploit with materials from a hardware store. And there are 3 natural mechanisms that make it possible without any electricity at all. The first is radiative cooling. At night, surfaces radiate their heat into the cold sky and drop below the ambient air temperature. A thin sheet of plastic or metal, insulated from the ground so it cannot absorb warmth from below, can cool 5 to 15 degrees below air temperature with zero energy input. The second mechanism is condensation on thermal mass. Cool rocks and dense surfaces collect moisture as warm, humid air passes over them during the day. The third is fog and mist interception. Mesh or netting physically captures suspended water droplets from moving air. No condensation required. These 3 mechanisms have been understood and exploited for centuries, long before anyone had electricity or modern engineering. And the civilizations that used them did not treat water as a commodity. They treated it as something the atmosphere simply gives you, if you know how to ask. The Inca Empire sustained entire cities built above the rain line by collecting dew and channeling it into cisterns. They used fog fences, essentially mesh barriers stretched across mountain ridges, to intercept moisture from clouds that rolled through. No electricity, no moving parts, just a deep understanding of how water behaves in the atmosphere. In 1900, a Russian engineer named Friedrich Seibold discovered 13 massive stone piles near the ancient Byzantine city of Theodosia in modern-day Crimea. Each pile covered 900 square meters and stood 10 meters tall, connected to terracotta pipes that led directly to city fountains. Seibold concluded these were ancient dew condensers that had supplied the entire city with water, and he calculated they could have produced over 55,000 liters per day per pile. He was so convinced that he built his own replica in 1912, a 20-meter wide truncated cone of sea stones standing 6 meters high. It produced an estimated 360 liters per day until the base developed leaks in 1915. Later researchers in the 1990s determined the original stone piles were likely ancient burial mounds, not water systems. But here is the critical detail that gets lost in that correction. Seibold's replica actually worked. It produced real water, partly through fog interception and partly through radiative cooling of the surface stones. The history was wrong. The physics was right. In the 1930s, Belgian engineer Achille Knoppen built a massive 14-meter-tall stone tower in Aix-en-Provence, France. Walls 3 meters thick, riddled with air vents. Inside, a concrete column studded with slate projections designed to maximize condensation surface area. The theory was elegant. The structure would cool overnight. Warm, humid air would enter during the day, condense on the cool internal surfaces, and drip down to collection basins. The tower still stands today, in ruins. It produced only a few liters per day. A spectacular, expensive failure. The reason it failed is the single most important lesson for anyone trying to build their own system. High-mass structures do not work. You simply cannot shed enough heat overnight from massive masonry. The thermal inertia is too great. The stone absorbs heat all day and barely cools by morning. Early 20th century engineers understood the physics perfectly, but they got the implementation exactly backwards. A German chemist named Wolf Klapphake understood this in the 1920s and the 1930s. Instead of building monuments, he cleared and smoothed mountain slopes, then shaded them with simple, lightweight canopies. At night, the slope cooled rapidly. During the day, moisture collected on the cool surface beneath the shade. Klapphake wrote that it was wrong to think this process only works on days with visible dew, because the shaded inner surface becomes much cooler than one should expect. In Dalmatia, he reported a day that failed to produce water was the rare exception, not the rule. Klapphake proved something that should have changed everything. Simplicity beats complexity. Thin, light surfaces that lose heat quickly will always outperform massive stone monuments. That insight is the foundation of every practical system that follows, and it is exactly the insight the commercial industry would prefer you never internalize, because it means you do not need their products. Here is the first system you can build for about $8 to $12, a radiative dew condenser. You need a polyethylene sheet or a thin metal sheet for the condenser surface, about $3 to $5. Polystyrene foam insulation for backing, $3 to $4. A simple frame of wood or PVC pipe, angled at 30 degrees, $2 to $3. And a collection gutter cut from PVC pipe or aluminum channel. Mount the sheet at a 30-degree angle on the frame, elevated 2 to 3 feet above the ground so ground heat cannot reach it. Back it with insulation. At night, the sheet radiates heat to the sky, drops below the dew point, and water condenses directly on the surface. It runs down the angle into the gutter and into your collection container. Expected yield is about 0.3 to 0.6 liters per square meter per night in favorable conditions. A 550 square meter installation in northwest India produces roughly 9,000 liters per year for a school. The thinner and lighter the surface, the better it performs. That is the exact opposite of what the monument builders tried, and it is why a $12 sheet of plastic succeeds where a 14-meter stone tower failed. The second system costs about $5 to $8. This is a solar still. Dig a pit about 16 inches wide and 12 inches deep. Place a collection container at the bottom center. Cover the pit with clear plastic sheeting and seal the edges with dirt and rocks. Place a small stone in the center so the plastic forms an inverted cone that points down toward the container. Solar heat evaporates ground moisture, and that moisture condenses on the cooler underside of the plastic and drips into the container. You can pour dirty water, salt water, or contaminated water into the pit to dramatically increase yield because the still purifies the water through evaporation and condensation. The output is distilled water. Expected yield is between 100 and 150 milliliters per day from a single pit. Multiple pits scale linearly. The third system costs $8 to $12. A fog and dew mesh collector. Stretch shade cloth or fine mesh netting vertically between two poles, perpendicular to the prevailing wind. Mount a gutter along the bottom. Wind-driven fog deposits water droplets on the mesh filaments. Droplets coalesce, and water runs down into the trough. A 1987 project in Chile used 48 square meter nets to yield enough water for 300 villagers. A system in Morocco improved on those early designs by 500%. Nature solved this engineering problem long before any human attempted it. The Namib Desert fog basking beetle survives in one of the driest places on Earth by standing at a 23-degree angle, facing into the fog wind. Its back has alternating hydrophilic bumps that attract water and hydrophobic troughs that channel droplets toward its mouth. Researchers at MIT have mimicked this design with textured surfaces that dramatically outperform simple netting. Redwood forests survive on limited rainfall because fog condenses on needles and drips into root systems, a natural fog collector operating at the scale of an entire ecosystem. The research on scaling this technology is extraordinary and accelerating. A 2021 study in Nature modeled global potential and found that atmospheric water harvesters could provide safe drinking water to over 1 billion people. In 2022, researchers created a cellulose and konjac gum gel that produces 13 liters of water per kilogram of material per day at just 30% humidity. In 2024, MIT built a device using copper fins coated in zeolite that produces nearly 6 liters per day per kilogram of material. DARPA is currently funding a portable device designed to supply water for 150 soldiers from air alone. There are honest limitations. These systems work best above 30% humidity and 18 degrees Celsius. Radiative condensers only work at night. Solar stills only work during the day. Fog collectors need fog and wind. The smartest approach is to combine all three. Water quality is a real concern, as dew and fog water can carry airborne contaminants, so filter and treat before drinking. A single small unit will not replace your tap water. Think supplemental. Think garden irrigation, emergency preparedness, off-grid living, or proof of concept that you can expand. Multiple units scale linearly. Remember the lesson of every failed monument in history: go thin, light, and insulated. The atmosphere is an ocean of water above your head, 12,900 cubic kilometers of it. Engineers from the Incas to MIT have been extracting it for centuries. The physics is not complicated. Cool a surface below the dew point and water appears. For $12 and a single afternoon, you can build a working system that pulls water from thin air. No electricity, no plumbing, no moving parts. The same principles that sustained ancient cities. The commercial industry charges thousands for devices built on the same physics. The materials cost almost nothing. The knowledge has been publicly available for over 100 years. The question was never whether this works. The question is why it disappeared from common knowledge, and who benefits from making sure you never learn how simple it really is.